Okay, so welcome back to day 2 of section 4.1 and 4.3. So today, before I get into any of the new content, let's do an example just to review. Let's say I have this function, f of x equals square root of x minus fourth root of x. And let's find the local extrema. So that is the local minimum and maximum. So first thing that might be useful is, what is the domain? Well, you have a square root and a fourth root. You can't put negative numbers in there. So you get that its domain is going to be 0, infinity. Now notice that 0 is a left endpoint for the domain, so we're not going to say that it is a local maximum or minimum. So if I want to do the first derivative test here to find what its maximums and minimums are, I want the first derivative of this thing, which, remember, this one is going to be x to the 1/2, x to the 1/4. So by doing the power rule, we get 1/2 x to the negative 1/2 minus 1/4 x to the negative 3/4, or rewritten 1 over 2 square root of x minus 1 over 4 fourth root of x cubed. Now notice that the derivative is only undefined at numbers that are less than or equal to 0. However, numbers that are less than 0 aren't even in our domain. And 0, we said, is not going to be, by convention, be a local extreme value because you don't have any points left of 0. So the only thing we need to do is solve where this is equal to 0. Well, to do that, you add second fraction to both sides. And then using some algebra, this is just 2 square root of x equals 4 fourth root of x cubed. And then you divide 2 by both sides. And what that will give you is that the square root of x equals 2 fourth root of x cubed. Apply a fourth power to both sides. On the right, you actually get x squared because you have a square root of square root raised to a squared power raised to another squared power. So that is squared and then squared again. And then equals 2 to the 4th. It's just going to be 16. And then fourth root and 4 cancel, giving you x cubed. So then x squared, and if you move the x squared to the other side and factor x squared out, you get 16x minus 1 equals 0. So x is either 0 or 1/16. And so let's erase this. That's your critical numbers. So we have 0 and 1/16. Like I said before, that you can't have any x values less than 0, so we don't even talk about those ones. But we can talk about 1/32 and x equals 1 for our first derivative test. And what do you get? Well, you have to plug those numbers into the first derivative, and you will get, this one is a negative, so downwards, and x equals 1, well, you're going to get up. This will give you a negative number, and this will give you a positive number. So what does that give us? Well, f of 1/16 is a local minimum. Okay. So far we've been just talking about the first derivative and talking about increasing and decreasing. And we want to think, is there any other information that we can talk about when talking about this sort of idea with looking at stuff with derivatives? So now we're going to talk about a different idea called concavity. So the idea with concavity is you could look at stuff that looks like this. Let's say these two appear in two different graphs. Notice that this one, it's sort of, if we draw the secant line, it's sort of it lies above, versus the secant line here, the graph lies below. So they have some difference. But if you just look at the first derivative test, you notice that both are increasing. Also, neither of them have any local maximum or minimum values. So with what we currently have, we can't really distinguish between the two, even though the two are very different graphs themselves. But to look at start to think about what their difference is, let's draw tangent lines along here. So if I draw the tangent line on the one on the left, notice that what I have is that our tangent lines are going from being positive to be positive, like this one, to being close to the zero, like this one. So our tangent line, the slope of the tangent line, that is the derivative, is decreasing. And when I see those two words, something and decreasing, sort of think back to the end of the last chapter when we were talking about related rates. When you see the word something decreasing, that means we're looking at some sort of derivative. But this is the derivative of the derivative, or second derivative. Similarly, you could draw, let's do it in red this time. You can draw the tangent lines. They're sort of starting out sort of more level, and they're getting steeper. So in other words, the derivative is increasing. And so there's words to describe these. The one on the left is called concave down, and the one on the right is called concave up. Which, if you think about it, that would make sense, because up being for increasing, down for decreasing. Now, if you look in the textbook, there's other definitions that you could talk about with this concavity, but that is what we're going with right now. And what this leads to, and this discussion about derivative decreasing, derivative increasing, that idea is what is known as the concavity test. If the second derivative is greater than 0 for all x values in an interval, then f is concave up. And if the second derivative is less than 0 for all x in an interval, f is concave down. Now, what about the other two cases? At a point, the second derivative could be undefined or 0. So here's just a definition. Well, we say that if f is continuous at a point, well, let's call this C, and its second derivative is 0, with f changing between concave up and concave down, then f of c is called an inflection point. So right now this is just sort of the abstract math language. Let's put a picture so that we can more accurately just get an idea, some intuition for what's happening. Now, there is supplemental videos today talking about this this concavity test. But before we do an example, let's do a graph example. So let's suppose this is x value of -2. Sorry for my crooked lines. This is 3. Let's say we have something like this. Oh. And then it switches to going in this shape until here, where it sort of levels off. Well, know that down here, the sort of shape we have is something like an upward parabola. And same over here. In those sort of areas where you see that upward parabola shape, we say that those areas are concave up. Versus here we have a downward parabola type shape. That would be concave down. Now note that I'm not saying that it has the exact shape of a downward parabola. It's just, in general, looks more closer to that shape. Now, at these 2 points, it's changing. So we would call these inflection points. And that's the picture to have in mind. Okay, so let's do an example. Let's do x to the 4th minus x cubed plus 1. And let's say that this problem asks you to find intervals of concavity and all the inflection points. Well, you take the first derivative. You get 4x cubed minus 3x squared plus 0. You take the second derivative, and what do you get? You get 12x squared minus 6x. Now, this is a polynomial. It is defined everywhere. So to find the possible inflection points, we set this equal to 0 and solve. You pull out 6x, you get 2x minus 1 equals 0. So x is either 0 or 1/2. Now we're going to set up a similar system that we had with the first derivative test for the concavity test. And we're going to test points again. So we can test -1, -1/4, and 1. Okay, so -1, we're plugging it into the second derivative. And what do we get? Well, we'll get 12 plus 6 is going to be positive. And x equals 1, you get 12 minus 6 is still positive. But if you plug in, sorry, that's a positive 1/4. If you plug in 1/4, you will get a negative number. So concave up, you have negative infinity to 0 and 1/2 to infinity, whereas concave down, you have 0 to 1/2. So that's an example, and in the supplemental videos on Canvas, there's a video for you to watch that is going to go through another example. Okay, so the last topic for this section, and we're going to do more examples tomorrow, but let's go through this topic, is what is known as the second derivative test, which is different from the concavity test, but related to the idea of concavity. So what the second derivative test says is suppose your second derivative is continuous. Near a point C. If your first derivative applied at C is 0, so that is C is a critical point, and your second derivative is greater than 0, then f of C is a local min. If you have the same conditions, but instead you have that f double prime of C is less than 0, And instead of local min, you'll get a local max. Now this seems sort of like a weird test to do, and it's really just an alternative to doing the first derivative test, but it does work. And to see why, let's look at the parabola. Y equals x squared, we know is its second derivative is going to be 2, which is greater than 0 everywhere. So this is going to be concave up. It's going to satisfy this condition with a critical value that C is going to be at x equals 0. So C equals 0. But we know that that is going to be a minimum. So just as a example, think x squared versus y equals negative x squared. When you flip it, its second derivative will be, second derivative will be less than 0. And at c equals 0, you get that it's a local max. So just as a sort of intuition on why this works. So let's go back to our polynomial example and test this out. Now, I'm never going to require you to use the second derivative test because the first derivative test give you the same thing with the local maximums and minimums. But let's just do an example just to see how this works. Going back to that x to the fourth minus x cubed plus 1. We can look at, well, if we want to find the local extreme values, we take the first derivative. 4x cubed minus 3x squared. And we could set that equal to 0 because it's defined everywhere. So factor x squared, 4x minus 3 equals 0. So at x equals 0 and x equals 3/4. Okay. So if we want to use the second derivative test, we take the second derivative. And that gives us 12x squared minus 6x. So then if we plug in 0, we get 0. Whereas if we plug in 3/4, we get 12 times 9/16 minus 6 times 3/4. And you could go to a calculator, but this is going to be, well, these two are both divisible by 2. You get 8 and 6, still divisible by 2. You get 4 and 3. So it's going to be 27/4 minus 18/4, which is going to be greater than 0. So because the theorem didn't say anything about when it's equal to 0, we can't conclude anything about this. We can't conclude anything about 0 being a local maximum or minimum, but what we do know is that f of 3/4 is a local minimum. And that's how this second derivative test works. There's supplemental videos on both concavity test and second derivative test that I expect you to watch. And tomorrow we'll just do more examples, and there will be a worksheet to be done on Canvas.